skyscraper threatens to rain solid rock down on Chicago.
A small piece were to fall from this building. It would cut through the air like a knife.
Tragedy strikes a groundbreaking Vancouver Bridge.
When I got there, it was chaos. There were rescuers combing through the wreckage of the bridge.
A Danish demolition catches everyone by surprise.
Everybody was in shock.
And in California, a railroad calamity with devastating consequences.
There was the engine laying on its side, and I observed numerous cars in the river.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. When engineering goes wrong, the cause of the calamity can be huge and obvious for all to see. But sometimes gigantic projects can be threatened by the smallest of flaws. Like this building in Chicago, where a beautiful addition was an ugly catastrophe in the making.
This could have been deadly for people on the streets below.
A layer of heavy marble covering the outside was a lethal disaster waiting to happen.
We're up there on the side of the building. We are shocked at the condition of the marble.
This building was designed to have high impact, just not like this.
The Windy City has long been famous for its bold architecture. With a skyline dominated by massive skyscrapers, the city has been home to the world's tallest building more than once.
For more than 100 years, Chicago and Manhattan have battled each other for the title of the greatest skyline, which usually meant the tallest building.
By the 1970s, thanks to huge leaps in structural engineering, Chicago led the world in skyscraper design. Master stonemason Robert Gerskis spent 3 years working on one of the city's tallest towers.
All right, here we go, ladies and gentlemen.
Although few know the story, Chicago's AON building has a very dramatic history.
Chicago traffic helicopter 1 by X-rays.
Completed in 1973, this 83-story skyscraper was the Standard Oil Company headquarters, known locally as Big Stan.
Beautiful, beautiful. Very nice.
When built, it was Chicago's tallest building and the 4th tallest in the world.
This is the building right here, formerly known as Standard Oil Building, 137 feet off the hard deck all the way up to the top. Right now, we're approximately 1,200 feet above ground level, and the views are spectacular. Totally awesome.
Big Stan wasn't just super tall. In engineering terms, it was a trailblazer. As architectural historian Rick Keel explains, it pioneered a new structural system.
The AON tower actually has the frame of the building and the support of the building in the outside wall. And the outside wall forms a giant square tube that goes up into the sky.
For decades, most towers were supported by columns spread evenly throughout the building. But for Big Stan, architects placed steel columns in tightly packed rows around the outside, known as a tube frame, with a central core of columns.
That tube is then tied across between the floors to the center elevator core, which gives it more strength.
Tube-framed towers could resist greater lateral forces from high winds or earthquakes than their predecessors, allowing them to grow taller. With Big Stan, the columns were long, slender triangles running the full height of the tower, interspersed with narrow windows. But the architect had bigger plans beyond the revolutionary steel skeleton.
As well as innovating the internal structure, the architects wanted to create an iconic exterior that truly shone in the skyline.
That shine came from one of the most ambitious cosmetic jobs since the Great Pyramid of Giza. All 83 stories of steel would be covered with top-of-the-line Carrara marble from northern Italy. As material scientist Laura Powers explains, marble has a long history in construction when appearance is a priority.
Carrara marble is a wonderful stone. It was Michelangelo's marble of choice for sculpting because it is so pure, it's very predictable when you're working with it. Because it is such a special stone, when someone wants to make a statement, they'll use Carrara marble.
Marble can be highly polished and solid blocks will last centuries. But structurally, Big Stan didn't need any more support, and so the outside was purely aesthetic.
To achieve the designer's intended look, Big Stan took advantage of the latest engineering advances in rock cutting. The plan was to cover the triangular columns with thin sheets of marble, just over 3 centimeters thick, running from street level to the top, 83 stories above. In all, it took 43,000 panels, each weighing as much as a motorcycle. In 1973, when Big Stan opened its doors for business, it was the tallest marble-covered building in the world. But just a decade later, the shine began to fade. Routine inspections revealed that the slick marble coat was cracking and in danger of crashing down to the ground. This is where restoration specialist Robert Gerskis came in. He captured this unique footage as he assessed the damage.
We're up there on the side of the building. We are shocked at the condition of the marble.
The fear was that the sheets of rock, as heavy as 2 men, could have fallen from 80 stories up.
As early as the construction phase, there were reports that the marble was not secure.
It's reported that on Christmas Day in 1973, one of the slabs fell from Big Stan, and it pierced the roof of the neighboring office. The fact that it happened on a public holiday might have been a blessing in disguise.
This is the actual piece from the AON buildings. Full panel, typical panel is like 4 foot by 5 foot. This is about 11-pound piece right here, 1,000 feet up in the air, all the way down to the ground. This would do some serious damage.
So, why was the same type of marble that had lasted over 500 years in Italy struggling after less than 20 in Chicago? It seems thin sheets of marble and the Chicago climate were a bad combination. Structural engineer Michael Scheffler analyzed the damage in the 1980s.
Well, it had proven the test of time in Italy. Italy has a very benign environment. Chicago has a much different climate than Italy. In Chicago in the winter, you can get below 0, and you can get up to 100 degrees. And this had a profound effect on the material's behavior.
The problem was something called thermal hysteresis, which basically means an irreversible bending or bowing out of a panel caused by temperature change.
With the building known as Big Stan exposed to the extremes of Chicago weather, the outside of the panels were repeatedly heated or cooled more dramatically than the inside. This gradually and permanently altered the internal structure of the marble, causing the panels to bow outwards.
They were beginning to warp and pronounced bowing outward as much as 1.5 inches at the center of the panel in a 4-foot 2-inch height.
But thermal hysteresis wasn't just bowing the panels. As they deformed, they became more vulnerable to extreme weather.
To make things worse, that weakness was allowing water in, which was doing even more damage as it froze and expanded in Chicago's winters.
Carrara marble is composed almost entirely of calcite. Because the calcite in this marble expands in one direction more than it expands in another direction, it breaks the contacts between the crystals, so water can get in. And in a climate like Chicago's, when water gets in and subsequently freezes, the expansion of that water can tear the stone apart. These two images from the microscope show Carrara marble. The image on the right is showing Carrara marble that has never been exposed to thermal cycling or to freeze-thaw cycles. And the one on the left shows Carrara marble that has been through thermal cycling. This is similar to the marble cladding on the AON building. So in the damaged marble on the left that has been through the cycling, the heavier blue lines are showing micro cracks that are attributed to freezing and thawing distress.
Many of the panels were experiencing cracking and spalling at their connections. It was revealed through testing that the material had lost, in some cases, as much as 90% of its strength.
Not only did it spoil the clean lines, but there was a real risk that the panels could literally pop themselves off the building.
In the 1980s, with the cracking on the marble facade getting worse, something had to be done to protect the people below. A very temporary solution was found until a complete redesign could be put into place. Stone restoration specialist Robert Gerskis explains.
This building was a total challenge because we had to put on straps on over 43,000 pieces of marble. If it wasn't for the straps holding on to marble on the side of the building, we would have a huge problem. Pieces probably would fall off.
The ultimate solution was just as bold as the original design. Robert was one of the master stonemasons tasked with replacing all 43,000 heavy marble panels.
This job was just massive in its undertaking. This is the largest, probably the biggest recladding job, the tallest recladding job in the world at the time.
The audacious plan was to recover the entire building in a much tougher Chicago weatherproof stone, granite.
We started recladding in 1988. We had to take off 43,000 pieces of marble and replace it with 43,000 pieces of granite, all done on the outside, and the building is still occupied. They did not shut down the building. So the people that worked on this building had to be the best of the best in the business.
Replacing the heavy panels more than 300 meters up in high winds was more than just a technical challenge for Robert and his team.
And sometimes we had to contend with very, very high winds. It was very, very scary. You had to be aware of your surroundings. And with that being said, courage is learning how to manage your fear.
By 1992, after nearly 4 years, the biggest renovation on one of the tallest buildings in the world was finally complete. None of the precious marble went to waste. It was crushed and used to landscape a nearby oil refinery.
Replacing the thousands and thousands of panels is said to have cost $80 million, nearly half the original construction cost. But nearly 30 years later, the cladding is still going strong.
While the drastic solution was expensive, it was a huge success. And since Big Stan's original high-class cladding catastrophe, architects and engineers no longer use Carrara marble for external coverings anywhere in the US. With big engineering, overcoming gravity is always a key consideration. But when your very stability is under threat, every calculation is vital. Like this bridge in Canada, which was hit by a disaster that left a nation reeling.
This was the worst industrial accident in Vancouver's history.
An engineering catastrophe with devastating consequences.
Had I been there that day, I wouldn't be here today.
This tragedy left a lasting mark on everyone involved.
I wake up, I can still see that, even after 62 years.
Vancouver, on Canada's Pacific coast, is a bustling seaport. It was established in 1792 by George Vancouver, around the natural harbour he named the Burrard Inlet.
The Burrard Inlet is a shallow fjord carved by ice that separates downtown Vancouver from the Pacific mountain range to the north. It's a sheltered inlet and ideal for shipping.
To keep things moving on and off the water, bridges have long crossed this busy shipping lane.
There have been bridges across this stretch of water since the 1920s, but all have proved problematic.
The main flaw was with the section between the main supports, the central span of the bridge.
The first bridge was hit by several ships. One even got wedged beneath it, ripping away its center span.
Repaired and reopened, the new bridge had a centre lift span, which brought problems of its own.
The new span had a lifting mechanism to allow ships through, but became legendary for its traffic delays. In 1 year alone, the central span was raised over 5,000 times.
By the 1950s, it was clear that a completely new bridge was needed. Luc Lessard moved to town to work as a foreman on the new crossing, called the Second Narrows Bridge.
In 1957, I moved from Quebec to Vancouver. The beauty of Vancouver, when I arrived, I was amazed. The purpose of building a new bridge, the Second Narrow Bridge, was because the traffic increased, plus the boat and the ship coming underneath, they were getting higher and bigger all the time, and they need more water clearance.
The best solution for both increased traffic and larger ships was a cantilever bridge.
A cantilever is effectively a bridge where each span is only anchored or supported at one end, while the other end projects out like a long arm across the water until it meets the section from the other side.
Yet this one was a little different. Many cantilever bridges stand on large supporting piers with the steelwork pointing skywards. But here, to get maximum height for shipping, this one was effectively flipped upside down, with the road deck running on top.
The new design did away with both the problems of its predecessor. It would be high enough to allow large ships to pass underneath, while traffic could continue to flow on the road above.
At the time, Peter Hall was a young draftsman when he was asked to film the construction.
I didn't own a movie camera, and never having used one before, I borrowed one from one of the fellows in the drawing office.
Building this towering structure was no easy feat. Luke and his team of ironworkers were often doing back-breaking work more than 30 meters in the air, and Peter was right up there with them.
The work of a bridgeman or an iron worker is a very dangerous job because most of the time we work on the air. Any fall, we know that be our life. And those days especially, we did not use a safety net or cable or tie down. We were completely free walking on any piece of the bridge.
Back then, men were walking across steel beams high in the air with no safety nets, no harnesses. This was a seriously dangerous occupation. These workers put their lives on the lines every day.
One of the biggest challenges for the ironworkers was that this type of bridge is unstable during construction.
The benefit of a cantilever bridge is that once complete, it's strong and stable enough to cross a large expanse of water. But the downside is that they're tricky to build.
With this upside-down cantilever, Vancouver's second Narrows Bridge couldn't support itself until each span was complete. So workers installed temporary structures called falseworks to support the span. Once a span was complete, it was fully self-supporting and the falsework would be removed.
This was going to be a jewel in the crown for construction in Canada. But then things went very wrong.
As Vancouver's new bridge took shape, on June 17, 1958, foreman Luc Lessard and his team were lifting a 55-ton section into place. Less than an hour before quitting time, without warning, the span collapsed. "79 workers, including Luc, fell more than 30 meters into the water."
We heard a big noise. So the bridge went down underneath our feet. First thing I remember, I was on the bottom of the ocean, 35 feet below the top of the water. Then I finally saw a light coming up from the sun through the water. I managed to get above the water. My leg and my arm was broken.
Peter Hall was lucky. He'd been called to the office earlier that day.
June the 17th, 1958. Started out like any other day. I was able to see the bridge from the top of the hill. And as I looked at the bridge, it was in the water. When I got there, it was chaos. There was bodies in the water, bodies trapped in the steelwork. I just couldn't film a lot of what I was witnessing. A lot of the people that were being brought off the bridge, I classed as friends.
Despite breaking his arm, leg, and his back, foreman Luc was one of the lucky ones. 18 of the 79 workers that fell that afternoon perished. In the wake of the tragedy, the official report concluded that there was a design and calculation error in a crucial part of the falsework. It seems the layout of the temporary arm beneath the fifth span of the bridge was fatally flawed.
The steel was bracing the heavy span of the bridge until a new section was fitted, but the exact layout of the falsework wasn't stable enough to support the weight of the incomplete bridge above.
As the new section was being moved into place, the falsework gave way, taking that whole section of the bridge with it. Bridge engineer Daryl Matson explains further.
The steel had lots of strength, but it lacks stability. There is no set calculation method for falsework short of it has to be big enough to hold the load and it has to be stable.
The heart of the problem was using a row of beams as a base for the falsework.
This is very much like if you take and you stack a whole pile of blocks one on top of the other. There's not really a strong connection between the blocks, and eventually they'll fall over. This is the same thing where we have the bridge sitting on top of a block, which is this column, sitting on top of another block, which is the beams. The problem with this is that there wasn't any stability to that lower block. Like, it wasn't even like I have a block that's this big that takes a bit to roll. They're very thin webs that just rolled over and flopped over.
This was the worst industrial accident in Vancouver's history, and one which perhaps could have been avoided with a relatively simple solution.
Had they put bracing in at 4 locations, one on either side, either truss, and one at the support of the foundation and one at the support of the column, had they put 4 sets of bracing in, that's all it would have taken.
It's easy to say with hindsight, but it seems like a relatively minor adjustment could have prevented a major catastrophe.
The bridge was rebuilt and finally opened in 1960. In 1994, to honor the workers who lost their lives, it was officially renamed the Iron Workers Memorial Second Narrows Crossing.
Often in my mind, at night, I can see what was happening. I can still see that, even after 62 years.
120,000 vehicles drive over the bridge every day, which is both a tragic reminder and a testament to some truly courageous men and all that they've achieved.
With big engineering, the devil is in the details. Numbers are checked and double-checked. But sometimes even the best laid plans can go awry. Like this precision project in Denmark that took everyone by surprise.
When you're using more than 20 pounds of high explosives, you really hope you've got things right.
In 2018, a landmark demolition blown completely off course.
It stopped, and then it was going the wrong way, and everybody was in shock.
Experts and residents were left wondering what had gone wrong.
It's safe to say this demolition did not go to plan.
Vordingborg, in the south of Denmark, is an ancient port town and home to some iconic Scandinavian architecture.
The picturesque old ferry town of Vordingborg has buildings that date back to the 14th century. The Danes know how to build things at last.
As the shipping industry grew, so did the port, which was relocated to a new site across from the town's waterfront.
In recent years, the port has undergone massive development. The ambition is for the town to be one of the largest grain exporters in Europe.
The waterfront has long been towered over by a giant silo. The 53-meter tall structure was built strong to be able to contain the massive weight of hundreds of tons of grain. Like most silos, it was built as a cylinder.
The cylinder distributes forces evenly around the outside, allowing them to withstand much greater pressure than square shapes.
As the new industrial port was being developed, the old harbour, with its standout silo, was also in line for a makeover. Local journalist Kim Eriksson covered the story.
There's a lot of development in Vordingborg area with new bridges and new railroads. The silo hasn't been used for many years. Before it was used for animal feed. Because of development of the area, it was decided to demolish it.
A strong and stable cylinder is ideal for storage. But when the time comes for demolition, they're complicated structures to bring down.
Most buildings are held up by supporting columns that can be blasted away and the whole thing collapses like a concertina. But silos have solid walls with no natural weak points for blasting.
There was an added layer of complication. The silo stood next to the town's cultural centre and library. It was critical the tower fell in the right direction. So, like felling a tree, demolition experts chopped a wedge in the side, planning to force the silo to fall away from its neighbours and into a specially prepared landing zone.
Demolition by implosion might seem like the easiest way to knock down a structure, but with such a tall cylinder, the smallest mistake could escalate out of control.
Silos are very strong as complete structures, with the forces all nicely balanced. But like all cylinders, as soon as you remove a piece that disturbs the balance of the entire structure, it becomes unstable and unpredictable.
The blast was so complex, explosive experts spent 6 months preparing. April the 9th, 2018, Demolition Day. With cameras rolling, engineers cleared the exclusion zone.
On the day of the demolition, everything seemed to be okay, and there was a big safety area, and there was 2,000 people, I guess, over here and over on the other side of the sea. Everybody was very excited about it.
At 5 o'clock, the explosives were detonated.
When this explosion happened, the silo actually went the right way for a few seconds. And then it stopped, and then it was going the wrong way, and everybody was in shock.
Not only had the silo fallen the wrong way, the force of the impact had crushed the end of the library and cultural centre. Thankfully, as firefighter John Hansen discovered, the exclusion zone had kept people safely out of danger.
There was no people at this time in the building. Everyone who worked at the building have gone to home for holidays. It was good luck that nobody was hurt at the time.
The disaster was the talk of the town, and with the cultural centre in ruins, residents wanted answers.
With all that planning, it should have fallen neatly into the landing zone, but clearly something went horribly wrong.
So, why was the silo blown so spectacularly off course? Professor of Engineering Per Golterman has a theory to explain the chaos.
What I have here is a model of the Vordingborg silo. We have removed some of the concrete and we are going to blast it. I'll use my blasting finger here. We'll remove that, and this is what was supposed to happen.
The initial blast went as planned, but the precise way the silo started to collapse made the difference between success and failure.
What did happen was that these parts here started to be crushed, and when this uncrushed part hit the ground floor, that's when it started to go all the other way back, because all this concrete here has been destroyed.
Instead of immediately toppling, the silo slumped backwards, and as the top of the wedge hit the reinforced base, the kick made it fall in completely the wrong direction. And while the report into the disaster is still ongoing, Per believes the demolition could have been done differently in the first place.
One thing was, for instance, to take it down in steps. Instead of taking the whole thing in one go, he could have taken it in 2 or 3 goes. But of course, it would probably have cut 3 times as much and taken 3 times as long.
While it might not have been as spectacular, taking the silo down piece by piece was probably the best way to go.
Thankfully, no one was hurt. The cultural centre has been repaired, and Vordingborg's dockside has a large clear area for new development. When you're pushing the boundaries of engineering, catastrophe can hit before the build is even complete. But sometimes trouble can lie lurking for decades, waiting for the right moment to strike. Like this engineering failure in Northern California, on one of the nation's most hazardous stretches of railroad track.
Cantera was the most disastrous, one of the most costly, and it affected a lot of people.
An epic miscalculation that nearly destroyed an entire ecosystem.
I could see fish floating in the river, belly up, and it was an indication of what had happened.
Almost every living organism along a 40-mile stretch of river was wiped out.
In the late 1800s, railways became vital to America's prosperity. As the Southern Pacific Network grew across the western states, engineers faced some of the nation's toughest terrain.
The West Coast Railroad has connected Southern California with the Pacific Northwest for about 100 years. The route runs right past one of the tallest volcanic peaks in the US, Mount Shasta. It's stunning and a real headache for railroad engineers.
To avoid the mountainous terrain, the track was forced down into the Sacramento River Valley. Train historian John Signor worked on the railroad for more than 20 years.
One of the big obstacles for this part of the railroad was getting up and out of the Sacramento River Canyon. The railroad follows the Sacramento River up canyon in basically what's called a water grade on about a 1.7% grade. They got to a point where there wasn't any way to continue following the river. So they got to Cantera and they made a loop. They did a 180-degree curve and started up the canyon wall at the same gradient. The curvature that was there was pretty extreme, and it is for a modern railroad. Even today at 14 degrees, it's a pretty sharp curve.
The result? One of America's most challenging sections of rail track, the Cantera Loop. Not only is the curve very tight, this is the steepest climb in California's railroad system and demanded extra locomotives to overcome gravity. These were housed in a rail yard 8 kilometers south of the loop, in the small town of Dunsmuir that had sprung up with the arrival of the railway. But as local resident Louis Dewey explains, there was more to Dunsmuir than just a railroad siding.
One of the main reasons it was originally popular with tourists is because the train stopped here. And Dunsmuir is the hub of what used to be a blue ribbon trout stream.
With its great climate, superb fishing, and crystal clear mountain waters, Dunsmuir became a top tourist destination. In fact, the official city slogan is, "Home to the best water on earth."
For more than 100 years, Dunsmuir was one of California's best-kept secrets. But one night in the early 90s, the town became famous for all the wrong reasons. On the 14th of July 1991, an 1,800-meter-long freight train was traveling up the west coast from the San Francisco Bay Area to Portland.
The train was headed north up the twisting Sacramento River Canyon, and about 9:40, they were approaching Cantera Loop. The train had 97 cars, 11 loads, 86 empties, and 4,294 tons.
Thousands of trains go through Cantera Loop every year. But this time, something went disastrously wrong. The lead locomotive and 7 cars derailed and fell into the Sacramento River.
It's a 14-degree curve.
Railroad engineer Gary Mahon was one of the first at the scene.
As I pulled up here, there was the engine laying on its side, and I observed numerous cars in the river. It was dark. I noticed the tank car partially in the river, but I had no idea what was in it.
What was in the car was 86,000 liters of a highly toxic herbicide called metamsodium. Although no one knew it yet, this was very bad news. Attorney Donald R. Bitblit later worked on the case.
Metamsodium is classified as a biocide, which means it kills any living thing. When it mixes with the water and turns into a combination of hazardous substances that would go off into the atmosphere.
Few people have heard of metasodium, but it's one of the most widely used pesticides in the United States.
The so-called best water on Earth had been contaminated by this toxic train load. Hardware store owner Ron McLeod witnessed the devastation unfold.
When I looked at the river, it was kind of a greenish-brown color rather than the clear water that we typically see. And I could see fish floating in the river, belly up, and it was an indication of what had happened.
Almost every living organism between the Loop and Lake Shasta, 40 miles or 60 kilometers away, was poisoned. The river was so polluted, it was nearly 3 days before scientists were even allowed near the water.
In the coming days, more than 1 million fish died.
The river was closed, of course, immediately. People that had been coming up for 20 or 30 years as a family didn't come up the next year. And they didn't come up because, of course, they couldn't go do their fishing.
Luckily, no one was hurt, but this was the worst environmental disaster in California history, and a catastrophe for Dunsmuir. But thousands of trains had navigated the Kantara Loop for years, so questions were asked. Why did this one come off the rails so spectacularly? An official report concluded that the derailment was, in part, caused by the configuration of the 97-car train. With too many empty and light cars at the front, when it took the steep uphill curve, the rear of the train pulled back, causing a phenomenon known as stringlining.
Imagine this string is the train going round the curve. So long as the forces are balanced, it stays curved. But if the heavy weight at the back pulls against the front, then there's a giant tug of war, and bang, the lighter trains in between are pulled off the track. That's why it's called stringlining.
With the imbalance in the load, the train was primed to derail, and bad luck made sure that it did.
Here's a simulated train approaching the Kantara Loop. This is the car of the chemical metam sodium, an agricultural chemical. And the train was heading for the loop, and a curve oiler caught one of the locomotive wheels, and it slipped, then bent on it, dumping the car of metam sodium in the river.
Railroad engineer Gary Mahon thinks that as well as the weight distribution, a fault in the lead locomotive might have tipped things over the edge.
It was reported that the engine that was derailed and laying on its side had not been working properly. It was surging, which meant it was jerking the train. And unfortunately, it did that just as they started around this curve. If that engine surged and there was enough power up there to stringline the cars off the track, had it been running right, maybe the derailment would not have happened.
The restoration and cleanup led to the largest environmental settlement in state history. To keep it from ever happening again, a barrier was built to prevent cars from being stringlined into the river, and new regulations on train configuration were implemented.
Following the investigation, the Union Pacific limited the length of trains traveling along the canyon, reduced their speed, and upgraded the locomotives pulling the train.
Finally, action was taken to get the Sacramento River and Dunsmuir back on track.
The accident still ranks as the largest hazardous chemical spill in California. But thanks in part to a 3-year fishing ban, most species in the river have completely recovered.
Hopefully, lessons have been learned so something like this never happens again.